Hello everyone, today we will talk about Michaelis-Menten equation. So before that we should understand in any enzyme catalyzed reaction the first step is formation of enzyme substrate complex. A substrate binds to the active site of the enzyme and in turn enzyme stabilizes transition state of the reaction, transition state intermediate of the reaction. This forms CS complex, and then the transition state is splits down to product which liberates some energy, and enzyme product complex formation occurs. The product binds enzyme weakly in comparison to substrate, so product is easily replaced by new molecule of the substrate. As a result, reaction keep going on. So if we want to measure rate of the reaction for any enzyme catalyzed reaction, there are two ways. First way is to measure concentration of substrate, because when enzyme is catalyzing conversion of substrate into product, the concentration of substrate is always going down with respect to time, and the product concentration is always going up when you measure with reference of time. So either you can measure disappearance of the substrate or appearance of the product. So for example, if you are measuring appearance of the product, so product and you are measuring with respect to time, you get this kind of graph. It means initially at 0 time there is no reaction occurred, so product concentration would be 0. But with time more substrate molecule come and bind to the enzyme, form ES complex, then the enzyme convert that into product, so product concentration keep going up. So this graph keep going up and eventually it become constant. When it become constant, it means all enzyme molecule, they are saturated with the substrate. This is the case when you have a fixed concentration of enzyme and your substrate is present in unlimited concentration. So when all the active site of the substrate are saturated with the active site of the enzyme are saturated with the substrate, so you get a constant here. So this kind of reaction, initially this graph follows first order reaction. First order reaction means the rate of the reaction is directly dependent on concentration of the substrate, and eventually it falls flat, which shows zero order kinetics. Substrate concentration is always high, but there is no change beyond this point. There is no change in the rate of the reaction, so this is zero order kinetics here. So when we measure rate of the reaction, the most accurate value for rate of the reaction is the one which is the slope of tangent of this graph, and this rate of the reaction is calculated by change in product concentration divided by the total time the time enzyme has taken to form the product. So V naught, we represent this by V naught, which means initial rate of the reaction. So initial rate of the reaction would be P2 minus P1, the change in the product concentration within the given time. So that's how we calculate rate of the reaction, and we always take to have more precise value of rate of reaction, we always consider initial rate of the reaction, which is represented by V naught here. Now let's look at how concentration of different components of an enzyme catalyzed reaction changes with respect to time. For example, substrate, initially substrate concentration is high, so when enzyme start functioning, substrate goes down. So substrate always decreasing in the chemical mixture, reaction mixture. So this graph shows substrate concentration, so which goes down with respect to time, eventually it get adjusted. Product formation, as far as product formation is concerned, because in enzyme catalyzed reaction, product is always being accumulated, it keep increasing in concentration. So this graph shows the product is being increased in an enzyme catalyzed reaction, and in the reaction, enzyme is taken in fixed concentration. So enzyme initially, for example, you have this concentration of enzyme, the enzyme concentration goes down. Enzyme concentration will free enzyme concentration, because enzyme is present in form of ES complex. So free enzyme concentration will go down, and eventually when the reaction is finished, it will come back to its natural concentration, the initial concentration. Similarly, ES complex, at 0 time there is no ES complex. So ES complex with time it will increase it go up, remain constant. It remain constant only up to when you have enough substrate concentration available. When substrate is adjusted, ES complex also comes down. So that's how it represents concentration of different components of a enzyme catalyzed reaction with respect to time. Okay. Now we'll talk about single substrate enzyme catalyzed reaction, and we'll drive Michaelis-Menten equation for this. Michaelis-Menten assumption was made in order to evaluate enzyme kinetics. As per this assumption, the formation of enzyme substrate complex leads to enzyme and substrate complex leads to ES complex, and this ES complex is converted into product and free enzyme. So in this equation, the formation of ES complex remains at equilibrium. The rate of formation of product is negligible. That was the major point of this hypothesis, that breakdown of ES complex into product is too little in order to disturb equilibrium of this ES complex formation from E and S, and it is splitting into E and S. So that was the major concept of this hypothesis, and it was also a drawback because as per this assumption, the formation of product is too little in comparison to ES complex formation or ES complex breakdown. So Michaelis-Menten considered that this rate constant K2, which is for formation of product, is too little to disturb the splitting of ES complex in this direction, and that's why ES complex formation remains at equilibrium by reaction between enzyme and substrate. This is the rate of ES complex formation, and ES breakdown into ES, which is designated by a rate constant K minus 1. So in other words, the ES complex remains at equilibrium. Means the formation of ES complex, the rate of formation of ES complex is equal to rate of breakdown of ES complex through K minus 1 rate constant. K2 is negligible in order to influence this equilibrium. So if we calculate the rate of formation of ES complex would be equal to K1. K1 is the rate constant for formation in the right hand side direction. K minus 1 is for splitting ES complex into ES. So rate of formation of ES complex is equal to K1, concentration of E and concentration of S. Similarly, breakdown, because breakdown as per this hypothesis, Michaelis-Menten hypothesis, assumption, the ES gets split down into E and S, and this splitting is not influenced much by this formation of product. So rate of breakdown of ES complex would be equal to K minus 1 concentration of ES complex. And as per the hypothesis, these two rates, they are equal. The formation of ES complex and breakdown, that's how ES remains at equilibrium. So we can put them together. K1 ES is equal to K minus 1 ES complex, and from here we can derive E concentration of E is free enzyme here, S is substrate. So ES divided by ES is equal to K minus 1 divided by K1. So K minus 1 divided by K1 is equilibrium constant for the ES complex, which is now called by Ks. So now the free enzyme in a chemical reaction, in enzymatic reaction, the concentration of free enzyme depends on how much enzyme being used in ES complex formation and how much total enzyme was there. So total enzyme concentration ET is equal to free enzyme, because some of the enzyme molecules remains in solution in free form, that is E, and some enzymes form complex with substrate and form ES complex. So total enzyme concentration ET is equal to E free plus enzyme involved in ES complex formation. From here you can derive value of free enzyme. So value of free enzyme E would be equal to ET, total enzyme used in the reaction, minus enzyme present in ES complex form. So E is equal to ET minus ES. So from here the value of free enzyme can be put in this equation. So Ks is equal to ET minus ES complex into S divided by ES. So from this equation it can be further simplified in order to get value of ES complex. So KSES is equal to ET minus ES into S, and further if you simplify this, the value of ES complex would be equal to ETS divided by Ks, which is equilibrium constant for ES complex, plus concentration of substrate. Overall rate of the reaction would depend on the slowest step of the reaction. So in this case, conversion of AS to product and free enzyme is the slowest step. So it means the rate of this overall reaction V0 would depend on this rate constant K2. So V0 is equal to K2 into ES. So it can further simplify. The value of ES complex can be put here, which we have just derived. So V0 would be equal to K2 ETS divided by Ks plus S. Then the maximum rate of the reaction is equal to, it depends on the total enzyme concentration we have taken in the reaction mixture, that is ET. So Vmax, the maximum rate a reaction can have, will depend on the total enzyme concentration and this rate constant K2. So Vmax is equal to K2 ET. So this K2 ET can be replaced by Vmax here. So V0 is equal to Vmax S divided by Ks plus S. This is Michaelis-Menten equation. The issue with the equation was that it has considered splitting of ES complex to product in a very low speed. So it was too low that it was not considered while drawing this equation. So that's why, but in many of the cases, many of the enzymes, we know that they have very rapid rate of the reaction. In that case, the K2 becomes significant, and when K2 becomes significant, the derivation would change, and it was done in 1925 by Briggs and Holden. So now we'll derive equation given by Briggs and Holden, which is a modified version of Michaelis-Menten equation. Briggs and Holden further modified Michaelis-Menten equation, and then they gave hypothesis which is known as steady state hypothesis. So as per this hypothesis, because in enzyme catalyzed reaction, enzyme concentration is too low and substrate concentration is very high. So enzyme ES complex formation, enzyme and substrate complex formation remains at a steady state by splitting ES complex into substrate and enzyme, and same time conversion to product and free enzyme is also significant. So rate of formation of ES complex as per this hypothesis would be K1ES. This is rate of formation, and because ES complex formation remain at a steady state, it means the breakdown would be equal to the formation. So the rate of breakdown will be equal to K minus 1 EMS, and because same time is breaking down into product also, so it plus K2 ES. So this is the difference which was considered by Briggs and Holden. So they considered splitting of ES complex for product also significant, the rate constant significant to disturb this equilibrium, disturb this steady state. So because being into steady state, both the rates would be equal. So rate of breakdown of ES complex would be equal to rate of formation, and if you keep them together, a new rate constant has been added, which is called K2 here. So if you bring them together, so concentration of ES divided by ES would be equal to K minus 1 plus K2, K minus 1 plus K2 divided by K1. And now this is called Km. Km is Michaelis constant. So Km, then the rest of the reaction, rest of the equation can be derived as per Michaelis-Menten. We have just done that. So finally the value of rate of the reaction, the overall rate of the reaction V0 would be equal to Vmax into S, concentration of substrate, divided by Km. Instead of Ks, it was Ks in case of Michaelis-Menten equation, but now it will become Km plus S. And in this reaction, when substrate concentration is very high, it means this substrate here would be called S0. S0 means the initial substrate concentration. Because enzyme concentration is too little and substrate is very high, the value of S would be S0, which is initial substrate concentration taken into consideration. So rate of the reaction would depend on initial substrate concentration and Km. Km is a Michaelis constant for the reaction. So the equilibrium assumption given by Michaelis-Menten can be only applied if the value of K minus 1 is very high, much more than K2. It means the dissociation of AS2 product is negligible. Only then equilibrium kinetics, equilibrium assumption given by Michaelis-Menten is applied. Otherwise, most of the reaction they are satisfied, they follow steady state kinetics given by Briggs and Halden. The value of Michaelis constant, Michaelis-Menten constant, no. The value of Km can be derived considering substrate concentration at half Vmax. So for enzyme catalyzed reaction, when you keep increasing substrate concentration, having fixed concentration of enzyme, you get this kind of graph. So here the maximum rate of the reaction attained by that enzyme concentration is called Vmax, and the substrate required to have half value of the Vmax is called Km. So for example, if this is half Vmax, at half Vmax the substrate required is equal to value of Km. So this can be derived from Michaelis-Menten equation. V naught is equal to Vmax S naught divided by Km plus S naught. So at half Vmax, when you have half value of Vmax, so half Vmax is equal to Vmax S naught divided by Km plus S naught. So you can simplify this, Vmax can be cancelled out. So 2 S naught is equal to Km plus S naught. So 2 S naught minus S naught is equal to 1 S naught, which is equal to Km. So at half Vmax, the concentration of substrate gives the value of Km, which is Michaelis constant. Direct measurement of catalytic productivity of a product formation of an enzyme catalyzed reaction is denoted by turnover number. Turnover number, which is shown by kcat. So kcat is basically maximum number of substrate molecule which are converted into product per unit time by per molecule of enzyme. Means one molecule of enzyme, how many substrate molecule it can convert into product per unit time. This is basically called turnover number. Kcat experimentally is equal to the K2, the rate constant K2. So kcat is equal to K2, and Vmax, we know that Vmax depend on the K2. So K2 can be derived as kcat. So Vmax is equal to kcat into ET, total enzyme concentration, and the larger the kcat, if for an enzyme if larger value of kcat is there, it means the reaction speed is very high. It can convert many more number of substrate into product per unit time per molecule of the enzyme. And when Km is much more than substrate concentration, when substrate is too little and Km is very high in comparison to the substrate concentration, the value of V naught can be derived from Michaelis-Menten equation, which will now be equal to kcat by Km, because Vmax is equal to kcat ET. So V naught is equal to kcat upon Km ET into S naught. So this kcat by Km is a new constant which is called catalytic efficiency. Higher catalytic efficiency means high value of kcat by Km means kcat should be more and Km should be less, because Michaelis constant Km shows lesser Km means high affinity of substrate to enzyme, and more kcat means more more efficient the reaction is, more rapid the reaction is. So a high value of kcat by km shows that the reaction is really occurring at very high speed. You require lesser substrate concentration to have a rapid rate of the reaction, and basically high number of this kcat by km also shows that if it is equal to the diffusion rate, not diffusion constant, which is around 10.8 to 10.7 per mole per second, it means the reaction is occurring at a level of diffusion of molecules in solution. Km can be used for different purposes for biochemical reactions, like it is used for measurement of affinity of substrate. So the value of Km shows the affinity between substrate and enzyme. Higher value of Km means the affinity between substrate and enzyme is less. Lower Km value means you require lesser substrate in order to attain half of the Vmax. It means the affinity for enzyme is high. And strength of the substrate binding. If Km is high, it means the binding strength is weak. If Km is low, the binding of substrate to the enzyme is high. Similarly, the value of Km also shows how much substrate is required for a significant catalysis to occur for any enzyme catalyzed reactions. Means if you want to see that how much substrate you begin with in order to perform some kinetics, you need to take substrate concentration which should be much more than the Km value of that enzyme in order so that the enzyme can catalyze the reaction and you can measure rate of the reaction. Km value also can be used for comparison of substrate for different enzymes. For example, in case of glucose phosphorylation, there are two enzymes, hexokinase and glucokinase. They both enzymes perform same function. They phosphorylate glucose and make glucose 6-phosphate. But if you look at the Km value for glucose, for glucokinase and hexokinase is different. Glucokinase has lesser Km value in comparison to hexokinase. It means glucokinase can perform its catalytic activity even much lesser concentration of glucose in comparison to hexokinase. And Km value also can be used to compare isoenzymes. Isoenzymes are protein enzyme molecules which have slight difference in their sequence, but they perform same function. They are located in different tissues, their location is different in tissues and cells, but they have the common product. But when you look at their Km value, the binding affinity of same substrate for different isozymes is different. So in order to compare different isozymes or identify isozymes, Km can be used.